We're all familiar with friction. It allows us to apply force to the ground to move forwards, it stops our cars from sliding sideways when we go around corners, and it lowers the efficiency of every machine you can think of, from wind turbines to blenders to steamships. We'll have a look at friction between dry surfaces and go through some examples. Dry friction always acts tangentially to the surfaces in contact, in a direction opposing motion or impending motion. As the force applied to a stationary mass increases, the friction force opposes it, maintaining equilibrium up to a maximum value. When the applied force exceeds this value, the mass begins to move. If we continue applying the force, the mass continues to move. If we remove the force, friction brings the mass to a halt. We're engineers, so we like quantifying things. How do we work out how much friction there is? Luckily, we have a formula to calculate friction between dry surfaces. F equals mu times n. We multiply the relevant coefficient of friction by the normal force, the force pushing the two surfaces together, acting perpendicular to the surfaces. The coefficient of friction is a measure of how well two materials stick together when they come into contact. Each pair of materials has two unique coefficients of friction. One is the static coefficient of friction, which is used on a stationary pair of materials to find the maximum force that can be applied to one of the materials just before it begins to move relative to the other one. The kinetic coefficient of friction is applied to a pair of materials in contact and already moving relative to each other. It is used in order to find the force required to keep the objects moving at the same velocity against the friction force. For a given pair of materials, the static coefficient of friction is usually larger than the kinetic coefficient of friction. Let's try an example. James is trying to pull his boat up onto his trailer. With the boat sitting stationary on the first section of the trailer, what is the minimum force required from the winching rope in order for the boat to start moving up onto the trailer? We'll assume a 1,000 kilogram boat, a static coefficient of friction between boat and trailer of 0.3, and the following angles. We state these angles relative to a set of coordinate axes. We'll also assume that the boat's center of mass lies along the line of the winching rope. Now we draw a free body diagram of the boat, showing it isolated from its surroundings, representing each force acting on the boat with a vector arrow. We know that friction acts tangentially to the surfaces in contact, but is the friction force acting up or down the ramp? We expect the boat to move up the ramp as the winch pulls, so we'll assume that friction acts down the ramp. Note that we haven't considered the size of the area of contact. This is because the magnitude of the friction force is independent of the area of contact, as long as neither surface dents the other. Our next step is to separate all of our forces into perpendicular components. Only the weight force is neither parallel nor perpendicular to the coordinate axes, so we need to break it down into a component parallel to the ramp with magnitude mg sine 30 degrees, and a component perpendicular to the ramp of magnitude mg cos 30 degrees. In order for the boat to remain in equilibrium, the forces along the x and y axes need to balance out. The sum of forces in the positive x direction is 0. Therefore, P equals F plus mg sine 30 degrees. We know the weight of the boat and the acceleration due to gravity, so we just need the magnitude of F. The boat is stationary, so we use the static coefficient of friction. We equate forces in the positive y direction and find n by subbing in values of m and g. We sub a normal force of 8,496 newtons into equation 2. We sub a friction force of 2,549 newtons into equation 1, and we find that a winching force of at least 7,454 newtons is required to get the boat to start moving up the ramp. Now we'll look at the boat a bit later on. James is in the process of winching it up the final section of the trailer. The winch no longer pulls the boat parallel to the trailer. The boat is being pulled up the ramp. If the coefficient of kinetic friction is 0.25, how much winching force is required to keep it moving? We start by drawing another free body diagram and a new set of coordinate axes. We resolve both the weight force and the winching force into components parallel or perpendicular to the coordinate axes. To continue moving at a fixed velocity, the forces on the boat must be in equilibrium. First, we balance the forces in the positive x direction, which gives us P equals to F plus mg sine 10 degrees, all over cos 20 degrees. Next, we balance the forces in the positive y direction, which gives us P equals to mg cos 10 degrees minus n, all over sine 20 degrees. Now, equations 1 and 2 are both expressions for the value of P, so we can equate them. There are only two unknowns here, F and N. We have a second equation relating these unknowns. Therefore, we can solve these two equations simultaneously, in order to find the values of F and N. Rearranging equation 3, we get an expression for F, which we can equate with equation 4. Next, we make n the subject of the equation. When we sub in known values, we find that the normal force is 8,287 newtons. More complex examples are fairly easy to find in your textbook. As engineers, you'll find friction both essential and sometimes frustrating. It brings the world to a halt and keeps us moving forwards.